Good afternoon, Valmiki. Good afternoon. Hello, my dear students. Good afternoon to one and all. Can you all able to hear my voice? Am I audible? Yes. Good afternoon. Good evening. Yeah. Can you able to see my screen? Yes. Okay. Okay. Fine. Thank you so much, students. So let's move on to today's session. Okay. So again, I'm going to give you a recall test for today's session also from the previous class. Okay. Students, is my voice clear to all of you? Some are saying it is not clear. Can others able to hear my voice clearly? Yeah, it is clear. Okay. Okay, fine. It is audible, no? Yeah. Okay, I'll speak a little bit louder also for you. No issues? Yeah, thank you. Thank you, students. Thank you. So now let's start. Okay, let's start. Okay, great. Great. So let's start with the recall test. Okay. So I have taken again two questions for this recall test. So here are those two questions for you. We are dealing with the solutions lesson. So the first question is, what is vapor pressure? And the second question is, you have to give me the formula for Raoult's law. Okay. So first, try the answer for first question. So let me know the answer in the chat box. Like, what is vapor pressure? Can anyone give me the answer for this question? All of you can try. All of you can try, and you can type the answer in the chat box. What is vapor pressure? In the last class, we have discussed about Henry's law, Raoult's law, etc. Right? So in that, I have discussed a term vapor pressure. Can anyone try the answer for this question? Measure of the tendency of a material to change into the gaseous or vapor state. Okay, pressure exerted by vapor in solid or liquid phase. Okay. If condensation is equal to vaporization, it is called vapor pressure. You have tendency to change into gaseous state. Very good, students. So many of you are giving me the correct answer for this question. So let us discuss. So the vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid. Okay, exactly. Many of you have given me the correct answer. Good. What about the second question? What is the formula for Raoult's law? You just need to give me the formula alone. What is the formula for Raoult's law? Very good, Nagashri. This P is equal to P naught into X. Great. So, in that formula, yeah, good, good. Very good, students. Good. So, in this formula, can anyone tell me what does the P naught denotes? What is the representation of P naught? P is the vapor pressure of the solution. What about P naught? What does this P naught denotes? Vapor pressure of the pure component. Priyanka, your answer is correct, but it never talks only about the solvent. It is the vapor pressure of the pure component. The component may be a solute or it can be a solvent, it can be anything. Okay. So it is not only about the solvent, it is the vapor pressure of the pure component. Very good. Very good, students. Good. So now let's move on to today's class. So the learning objectives for today's session is ideal and non-ideal solution. We are going to discuss about the azeotropic mixture. And at last, we have colligative properties. The ideal and non-ideal solution and azeotropic mixture will be the subtopics of Raoult's law only. Okay. So we were about to discuss this in previous class itself, but we could not able to complete that. We will try to cover it in today's session. Okay. Veera Prasad, am I audible now? So many people can be able to hear my voice clearly and it is audible for them. For some, it is not audible. Means you have to check your network connection. Yeah, now it is audible. Okay. Okay, students, let me start with the ideal and non-ideal solution. So first, let's go with ideal solution. Then we will discuss about non-ideal solution. Okay. So what is an ideal solution? The solution which obeys Raoult's law over the entire range of concentration. Okay. The solution which obeys Raoult's law over the entire range of concentration. So what is Raoult's law? It is P is equal to P naught into X. If I have two components, what I have to do is, suppose if I want to find out P1, then it is P1 naught into X1. Okay. If I have the second component, it is P2. It is equal to P2 naught into X2. So if something obeys this particular Raoult's law over the entire concentration, then we call those solutions as ideal solution. Okay. Now, if I have to find out the total vapor pressure, then I have to add these two. Right. P total is equal to P1 plus P2. So if I add these two, I will get an equation like this. Okay. So this will be the formula to find out the total vapor pressure from Raoult's law for ideal solution. So the definition is very important. Okay. You just have to have a look at it. Now, what I'm going to take, I'm going to have two molecules. So one is called molecule A and the other one is called as molecule B. Okay. Now let me take A first. So this is the A molecule. Okay. So you can able to see the interaction in a solvent molecule AA. Okay. And also I'm going to take a B molecule. B is a solute and A is a solvent. So in case of B, which is a solute, we have BB interaction in that molecule. Now, okay. Now, if I try to mix this solvent and solute, if I mix A and B, I will get a solute solvent molecule, right? In which I have A-B interaction. Am I right? Can you all able to accept this? So in one container, initially I have only A. So only AA interaction will be present. And the second beaker or second container, I will have only the B molecule. So I will have only BB interaction. Now if I mix A and B together, I will have AB interaction. All right. Now, if the solution is ideal, then the change in the enthalpy value, which is called as delta H, that will be equal to 0 because all the interactions are equal. Here you can see the equal to symbol, right? So AA interaction is equal to BB interaction, which is equal to AB interaction. So the initial and the final remain same. If the initial value and the final value remain same, in that case, if I take the change between those, what will be the answer? It will be 0, right? Suppose if I am trying to find out this delta H, what I will do? I will do the final enthalpy minus initial enthalpy. If final value and initial remains same, suppose if I have the value as 5. So final is also 5 and the initial value is also 5. Because they are same, then the 5 minus 5 will be equal to 0. So if the initial and final values remain same, if they are equal, then the change of those parameters will also be equal to 0. Okay. So delta H of the mixture is equal to 0. The same way, delta V of the mixture. Mixture in the sense the solute solvent mixture. Okay. So delta V mix is also equal to 0 for ideal solution. Now the very important thing is the examples for ideal solution. Solution of N-hexane and N-heptane is an example, one of the example. Benzene and toluene is the other example. Okay. The third example is bromoethane and chloroethane. So the examples are very, very, very important. Okay, because for NEET exam or JEE exam, they will give 4 options, right? They will ask you to find out the correct answer for ideal solution. So this example is very important. You should not skip this or you should not have any confusion with this. Got it? So only 3 examples are given in the book and they are going to ask question from NCERT only. So you need to memorize these 3 examples and the 3 points that you have to keep in your mind is first thing is the solution which obeys Raoult's law is called as ideal solution and all the interaction, all the forces of interaction is equal for ideal solution and the delta H mix and the delta V mix is equal to 0 and along with the examples, 3 examples. Okay. So these are the points you have to keep in mind for ideal solution. Is it clear for all of you? Shall I move on to the non-ideal solution? Do any of you have any doubts? No. Okay, fine. Now let's go for non-ideal solution. The solution which does not obey the Raoult's law over the entire range of concentration is called as non-ideal solution. Okay. So here the total pressure will not be equal to this P1 naught into X1 plus P2 naught into X2. Okay. Bira Prasad, only 3 combination of examples are given in the book. Okay. Just study only those because you will get questions only from those 3 things. Okay, you will not get any other example in your competitive examination. Okay, there are also some other examples, but it is out of our syllabus. Got it? So these are the main 3 examples which is given to us. All right. Shall I continue with the non-ideal? Okay, fine. Yeah. So, as I have told you, the solution which does not obey, which is not equal to, which does not follow this Raoult's law over the entire range of concentration is called a non-ideal solution. Again, I am going to take the molecule A, molecule B, and the interaction between A and B. So the first is A, which is a solvent molecule, and we have AA interaction in that. And in molecule B, in solute molecule, we have BB interaction. Now, if I mix these two, what I will get? I will get a solution, right? Now, here, the AA interaction and BB interaction will not be equal to AB interaction. Okay, so the final interaction is different from the initial molecules interaction. Okay, so if final is different from initial, then the delta H mix is not going to be equal to 0. So delta H is not equal to 0 and delta V is also not equal to 0. So all the enthalpy values, volume values, the change in enthalpy and volume will not be equal to 0. So this is about the non-ideal solution. Okay, this is about the non-ideal solution. Harish, you want me to explain this non-ideal solution once more? So the solution which does not obey Raoult's law is called as non-ideal. Okay, this is the definition. So how they are not going to obey this Raoult's law? So why and how? Their interactions will not be equal. The forces of interaction between the solute and solvent molecule will not be equal. Okay, in the previous case, in ideal solution case, all the interaction, solution interaction, solvent interaction, solute interaction, everything was equal. But here, the solution interaction is not going to be equal with the solvent and solute interaction. So if I try to take the delta H, so this is H2 is final and H1 is initial. H2 means it is for solution. This is the final part, right? So that is different from the initial. So it will not be equal to 0. So that's why that's why I have given it is not equal to 0. Yes, we reference that. I will come. So we do have some examples for non-ideal solutions also. So before giving the example, this non-ideal solution will again get classified. So into two. Okay, we do have different types of non-ideal solutions. Under each type, I will give you the examples. Okay, you're so enthusiastic. I know you're so curious about the examples which has to be covered here. I will give you. Don't worry. Harish, has your doubt got cleared? Have you understood about the non-ideal solution? Shall I move on to the next slide? Yes, very good. Okay. Now, this non-ideal solutions have two types. Okay, we do have two types of non-ideal solution. So, one is in accordance with positive deviation and the other one is with negative deviation. Okay. So, when do a system or a solution show positive deviation? In the non-ideal case, generally I told you that AB interaction is not equal to AA and BB, right? But more specifically, to talk about for positive deviation, this is the case. The force of interaction of AB will be less than AA and BB. Okay? If the AB interaction is less than AA and BB, then that particular solution will show positive deviation from Raoult's law. Okay? And if the case is opposite, means if AB interaction is more compared to AA and BB, then those solutions will show negative deviation. Okay. So if AB interaction is very less, AB is the final thing, right? AB interaction means this is the solutions interaction, which is the final. And A and BB are the reactants, means initial. So final is less compared to initial. So the total vapor pressure will be more compared to the initial. Okay, total vapor pressure will be more. And for the negative deviation, it is just the opposite. Okay. So if total pressure is more, if the total pressure is more, yeah, my dear students, I will give you the examples. Hemachandra from JNB Chittoor, I will give you. I told you, no. So we do have separate examples for non-ideal solutions. No, I will give you, don't worry. So for delta H mix will be greater than 0. Since the total pressure is greater than 0, delta H mix is greater than 0, and for the other case it is less than 0. Delta V mix is greater than 0, and for the other case it is less than 0. And delta S, what is meant by delta S? Change in entropy. S is called as entropy. So all these enthalpy, entropy, volume, temperature, all these terms you might have studied in your class 11 of thermodynamics lesson. Okay. So entropy is nothing but randomness. So that will also be greater than 0. And for negative deviation also it is greater than 0. Because it is called as entropy means randomness. Entropy is called as randomness. In both the cases, randomness will be more only. Okay. Once the solution is getting formed, the randomness of the molecules inside that solution will be more compared to the solute solvent. So in both the cases, it is greater than 0. Okay. And next, coming to the fourth factor, which is called as delta G mix. Delta G mix means it is standard Gibbs free energy. Change in the Gibbs free energy, it will be less than 0. It will be less than 0. Any example for entropy? So entropy means it is randomness. Okay, Harish. Randomness means suppose if I take solid, liquid, and gas. Solid means there will be regular arrangement of atoms, right? Yes or no? So to take an example, we can take water. Okay, water in the ice cube form, if you take, it is a solid. So we have regular arrangement of atoms in case of solid. But when you come to the liquid states, there will be some irregular arrangement. Molecules will be there, but it will be little bit irregular. But in case of gaseous state, so randomness is more. Okay. So in gaseous form, if I take the room, if I take your classroom, if I take my room in which I am living, so the room is a container, and the molecules which I am having inside this room, it will move here and there. Means the randomness will be more in case of gaseous state. Okay. Means the entropy of the gas is more compared to the entropy of the liquid compared to the entropy of the solid. Clear? If the randomness is more, entropy is more. That is the meaning. Then the change in entropy, which is called as delta S, is also more. Clear? You can compare the entropy. You cannot have some example for a particular system. Okay. Now the delta G should be less than 0 for both the cases. Only if delta G is less than 0, then the reaction will be spontaneous. Okay. If it is greater than 0 or if it is equal to 0, then it is non-spontaneous. Yeah, in both the cases, the randomness is increasing because we are mixing two components. Veera Prasad, we are mixing two components. We are mixing A and B in both the cases. Even though the force of interaction differs for both, the randomness will be increasing only, right? So I have a component A here. So here I have 1, 2, 3, 4. Okay. And this is my molecule A and this is B. So here also I have 4 molecules of B. Now what I'm going to do? I'm going to take the solute and mix it with the solvent. I'm going to take this A and mix it with B. So what happens in that case? So let me take this as, this is a hollow ball and this is a solid ball. Okay, so this is a hollow ball, solid ball. So what happens? The force of interaction may differ, but the randomness will be increasing, no? The regular arrangement of all the things will differ. Okay, clear. There is no relation between pressure and entropy, as far I know. Okay, so is that clear for you, my dear? When you are going to mix two things, you will have two components, A and B there. So in that case, the randomness will be more compared to the initial, in which you had only A and only B. Got it clear now? Yeah. So what are the things we have discussed here in this slide? There are two types of non-ideal. One is positive deviation and the other one is negative deviation. And five things, not five things, six things have been discussed here. So one is about the forces of interaction for both. The next is about the equation, total pressure. Then the remaining things are the parameters, okay? H, B, S, and G. So you should be very clear in all these parameters, which talks about the both the types, okay? It is not getting over here. We are going to continue this in the next slide also. Shall I move on to the next slide? Yes. Okay, okay. Yeah. Now coming to the examples, which you all have asked. Many of you know, you guys are very curious to know the examples of this non-ideal. So the non-ideal solution, which is showing the positive deviation, they do have some examples. The first example is a solution of ethanol and acetone. Second is the example of carbon disulfide and acetone. Okay. And coming to negative deviation, the first is the solution of phenol and aniline. Second is chloroform and acetone. Okay. So what you guys need to do, you have to memorize these examples. Okay. So we have studied three examples under ideal solution. And coming to non-ideal, for positive deviation 2 and negative deviation 2. Okay. So your job is to memorize all these things. Now let's see one graph. Yesterday, I have discussed one graph with you all. Do you guys remember that graph? With the vapor pressure and mole fraction. At this particular point, we have only the mole fraction of component 2. And at this particular line, we have only the mole fraction of component 1. So in this first line, I will have only the pure component 2, which is P2 naught. And in this line, I will have only the pure component 1. Okay. And if I connect P1 naught and P2 naught, yeah. So if I connect P1 naught and P2 naught, I will get the total vapor pressure. So I have discussed, right, something like this. Yesterday we have discussed. I have discussed with this green dotted lines with you all yesterday. Now all of you can able to see a red color line which is going above that green dotted line. Okay. So what does that represent? So it shows the positive deviation. Positive deviation means the line will go little bit above from the ideal solution line. So the green dotted line shows the ideal solution line and the red color line shows the positively deviated curve from the ideal solution. Okay, which is actually the non-ideal solution showing positive deviation. Okay. No, my dear. Chloroform means CHCl3. CCl4 means it is tetrahedral. Carbon tetrachloride, which is tetrahedral in shape. Okay. Chloroform formula is CHCl3. They will ask you the same examples only in the examination. Okay. So far, we did not get any other examples apart from this. Okay. So what I was saying. Yeah. So if the curve goes above to this ideal solution line, it is the positive deviation curve. Okay. So in the same way, if I draw the curve below the ideal solution line, then it shows the negative deviation. So very easy, no? Very simple and very easy. If it goes above, it is positive deviation. If it goes below, negative deviation. That's all. Okay, fine. So one of you are asking about type 1 and type 2. What do you mean by type 1 and type 2 in positive deviation, my dear student who is watching from user 32 ID? May I know your name, please? And I'm not clear about the doubt which you are asking. Positive deviation type 1 and type 2 means what do you mean? Okay, try to explain more clearly so that I can understand. Okay, you keep typing that. Before that, let me ask one question to all of you. I hope you guys have understood the ideal and non-ideal solution part. Okay. Using this concept, can you guys try the answer for this question? A non-ideal solution was prepared by mixing 30 ml chloroform and 50 ml acetone. The volume of mixture will be, which will be the correct answer among A, B, C, and D. A non-ideal solution was prepared by mixing 30 ml chloroform. So you guys are going for option B. Some of you are going for option A. A or B? Say any one now. B. So most of you are going for B. Negative deviation, so B. Answer is B. Okay, let's check the solution. Okay, so it is a mixture of chloroform and acetone. So chloroform and acetone mixture is an example for which deviation? Very good. It is an example for negative deviation, right? So for negative deviation, the delta V should be greater than 0 or less than 0. The change in volume. It should be greater than 0 or it should be less than 0. Very good. So it should be less than 0. Okay. So if I add V1 and V2, it should be less than 0. So 30 plus 50 is 80. So the correct answer is option B. Is that clear to all of you? People, those who have given option A as the answer, is that clear now? Okay. So this is how you have to apply the concepts which we are discussing in the class. Okay. So with this, I'm completing the ideal and non-ideal solution. Then the next is azeotropic mixture. Next topic, the second topic of today's class is azeotropic mixture. So it's very easy and simple. We can complete this within few minutes. Okay. So the first thing is I'm going to give you the definition for azeotropes. So what are azeotropes? They are the binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature. The solutions, the binary mixtures, they have same composition in liquid and vapor phase and boil at a constant temperature. Some of you guys are asking me some doubts. Let me go through that, right? In NCERT page number 84, the last line equation is not getting. Okay, now I don't have my NCERT book with me, JNV, right? So I will just go through it and I will let you know the answer in the next class, okay? Okay, yeah. At some point greater than even pure compound of user 32. What is your name, my dear? Venkata Surya. Yeah. Venkata Surya, I am not getting what you are trying to say actually. P total at some point greater than even pure compound of B. What do you mean by this? I don't get what you are trying to say. Okay, let's see. Let me go to the graph for you once again. Yeah, what is your doubt from this? So we have the pure component. So it is greater than, or it may be less than also. This P2 can be written here also, no issues. Okay, we have only one type for positive and negative, and in that type, we'll have a curve above the line, and in the other case, we'll have a curve below the line. You may have this point above or below, that is not an issue. Okay. Is it clear now? Am I clearing the doubt which you are expecting? If it is not, I will explain you in the next class, okay? So just explain, explain your doubt more clearly so that I can understand what you are coming to say. I am talking to Venkata Surya, okay? Yeah. Send me, Rajshul. I'll go through the book and let you know later, okay? Fine. So coming to this azeotropes. So what I was saying, yeah, it is a binary mixture having the same composition in liquid and vapor phase, and they boil at a constant temperature. So let me take a beaker. Okay. So I have a particle, I have a solution inside this. It is a binary mixture. Binary mixture means which has been composed of two molecules. One is A and the other one is B. Okay. It is a binary mixture. So now this mixture has same composition in liquid phase. So this phase is a liquid phase, no? The mole fraction of A and B in liquid phase is called as XA and XB. And the mole fraction of A and B in vapor phase is denoted as YA and YB. Okay. Now the composition of these two is going to be equal with the liquid and the vapor phase. Means XA is equal to YA, XB is equal to YB. XA and XB are the mole fraction of them in liquid phase, and YA and YB are the mole fraction of the components in vapor phase. Now, if they are equal, then those mixtures are called as azeotropes. Okay. And now I am going to give you some features or some important points of azeotropes. The first point is they boil at a constant temperature. They boil at a constant temperature. Okay. And they have the fixed composition. Composition will not change. It remains same. Okay. And the third thing is the separation of these components by fractional distillation method is not possible. You cannot separate the vapor phase component from the liquid phase component. Fractional distillation is a method in which we can separate two liquids. So that is not possible. Okay, separation is not possible for a azeotropic mixture. And the last thing is they behave as a pure liquid. They behave as a pure liquid. That's why we cannot able to separate them. Okay, so you have to keep all these 4 points in your mind regarding the azeotropes. The first thing is the definition. Definition is very important. Take down the definition, or if you're having your book with you, you can note down there also. Okay, Kaushik, YE and YB is not clear. Okay. XA, XB, you are clear about XA and XB, right? What is it? Mole fraction. Mole fraction of A and B. I already explained you what is mole fraction in the one of the class, right? While discussing the concentration term, we have discussed what is mole fraction. It is a number of moles of that particular component divided by the total number of moles. Now this is the liquid. This is a liquid, and I have two components in this liquid. I mean in the solution, in which the mole fraction of that A and B two components are denoted by the letter X. Now, if this liquid is producing the vapor, then the mole fraction in that vapor phase is denoted by the letter Y. Okay. Now it is called as Ya and Yb. Ya is the mole fraction of A in vapor phase. Yb is the mole fraction of B in vapor phase. Is that clear now? I hope it should be clear. Okay, students. Now, this azeotropic mixture is again classified into two. Means we have two types of azeotropes. Okay. One is called as minimum boiling azeotrope and the other one is called as maximum boiling azeotrope. So what is meant by minimum boiling azeotrope and which solution will show this? The solution which shows positive deviation is called as minimum boiling azeotrope. Okay. And the one which shows negative deviation will fall under maximum boiling azeotrope. So what are the examples of minimum boiling and maximum boiling? The examples are again very important. For minimum boiling azeotrope, which shows positive deviation, the examples are 95% ethanol and 5% water. Okay. And coming to this maximum boiling, it is 68% nitric acid with 32% water. Okay. So this mixture is important. So what is the formula for ethanol? It is C2H5OH with water. Percentage is also important. And nitric acid is HNO3 with water. Okay. Because in your examination, they will give the answers in terms of these formulas also. So you should know the formula for ethanol and nitric acid. And the boiling point is also important. For this, it is 351.2 and here it is 393.5 K. Got it? So here component A is ethanol and component B is water. Here component A is nitric acid and component B is water. So these mixtures, they boil at a constant temperature. Okay, and the composition remains same in liquid phase and vapor phase. Clear for all of you? The definition for azeotrope, two types of azeotrope. Okay, minimum boiling means positive, maximum boiling means negative, and the examples. One examples only we have in each case. Those examples with percentage and the boiling temperature is important. Is it clear to all of you? You're going to study these points under azeotropic mixture topic. Okay. So any doubt from the azeotropic mixture for anyone? Shall I summarize the today's session from which we have started? Yeah. So there are two types of solution. One is ideal, which obeys Raoult's law, and the other one is non-ideal, which does not obey Raoult's law. Okay, and later on we have discussed about azeotropes. In non-ideal, we had two types. Okay, one is positive and negative deviation, and azeotropic mixture means same composition, liquid and vapor phase. There also we had two types, minimum and maximum. So this is what I have discussed so far. Okay, since you guys have joined late for the today's session, I just want to extend this to 10 more minutes. Is that okay for all of you? You guys have joined at 4:20 only. No. So we have started the class very late. Shall I extend the class till 4:10 or 4:15? If you guys are okay with it. Okay, students. Fine. So without wasting the time, let me move on to the second half of the lesson. Okay, which is actually the colligative property. Which is called as colligative properties. Colligative property is the second half of the lesson. So here we will discuss about four colligative properties. Okay. How can they have minimum boiling point? In case of positive deviation, my dear, AB interaction is very less only, no? AB interaction is less. means the AB bonding is very less. The bond is not strong. It is weak only. So we can easily break that bond. The liquid will boil so easily, means it has only very minimum boiling point. Clear? The bond is not strong, my dear Wala. Got it? So in case of positive deviation, the A-B interaction is less only. That's what I have told you. No? Yeah. So if it is less, interaction is less, the interaction is less, means this bond is a weak bond. So it can easily break. They will boil immediately. Boiling point will be very less. I hope it is clear to you know. Okay, fine. Yeah, coming to this colligative property, it is one of the very important topic of this lesson, in which we are going to study some two formulas under each colligative property. Okay, and we are going to solve some questions also. Very easy, but very important. So before moving on to the types of colligative property, we'll just see the definition for colligative property. So colligative property depends on the number of solute particle. It depends on the number of solute particle and not on the identity of the solute particle. Identity means the nature. Identity means the nature of the solute particle. Okay. So what are colligative property? Colligative properties are the properties which depends on the number of the solute particle and not on the nature of the solute particle. Okay. How many number of particles present inside it? So accordingly, the property will change. That is the meaning. So we do have some types of colligative property. There are 4 types. One is relative lowering of vapor pressure. Second is elevation of boiling point. Third is depression of freezing point. Fourth is called as osmotic pressure. Okay. So these are the 4 types. Now to be more clear, I will take one example to make you understand this definition, and then we will look on to each and every type one by one. Okay. So moving on to the next thing, the example thing. Let me take an example. What I'm going to do, I'm going to add 1 mole of sucrose to 1 kilogram of water. And in the second case, I'm going to add 1 mole of urea to 1 kilogram of water. What do you guys think about this? Do you think the property will be same? Property in the sense the vapor pressure. Let me take vapor pressure as one of the property. Do you think the vapor pressure of water will remain same or it will differ? Very good, Sneha. It remains same. Decrease in the vapor pressure of water will be same. Why? Why? I am taking 1 kilogram of water in both the cases, but I am adding sucrose into 1 beaker and urea to another beaker of water. Substances are same, means the nature of the solute particle is, substances are different. The nature of the solute is different only. One is sucrose, the other one is urea. But the number, if you see, the number of that solute particle that remains same. Here also I am taking 1 mole and here also I am taking 1 mole. Okay. So the number of the solute particle remains same for both. So even though I have different solute molecules, since the number of the particle is same, 1 mole means how many particles will be there, my dear students? Avogadro number, right? So in 1 mole of any substance, I will have Avogadro number of particles, which is 6.022 into 10 to the power 23 particles, right? So in both the cases, in case of sucrose as well as in case of urea, we are going to have the same number of particles. So if the number of particles remains same, then the property also remains same. Okay. So because the number of particles are same in both the solutions. Got it. So this is about the colligative property introduction. Now let me enter into the relative lowering of vapor pressure topic. Okay, so let me continue this first type alone, and then I will finish off today's session. From next type onwards, we can discuss in the next class. Okay, tomorrow we will discuss. All right. So the first is relative lowering of vapor pressure, RLVP. Okay. Now, in all the four cases, first I will take the pure solvent component. Okay. First I will take a pure solvent. Now, the pressure exerted by this pure solvent is denoted by P1 naught. Why it is called as P1 naught? Solvent is denoted by 1. So I am putting 1 there, P1. So what is this naught represents? 0. It represents the vapor pressure of the pure solvent. Okay, I have only solvent molecule here. Means I have only the vapors of solvent here in the system, right? So all these particles are the particles of the vapors of solvent only. So P1 naught is the vapor pressure of the pure solvent. Okay. Now to this pure solvent 1, I'm going to add a non-volatile solute. The nature of the solvent is volatile. That's why it is getting evaporated. Volatile means something which is getting evaporated, right? Now to this, I am going to add a non-volatile solute. If I add a non-volatile solute, what will happen? You can able to see, right? The green color particles. Those are the solute particles. What will happen? The solute molecules are not going to come out from the beaker. Yeah, they will not come out from the beaker. Only the solvent molecules will come out. And also what the solute molecules will do, it will stop the solvent molecules which are coming out, right, by blocking. They will come and the green color solute particles will come and block the surface. Okay, and they will not allow the solvent molecule, more number of solvent molecules to come out. So here the solvent molecules might have come out easily, but here it will take some time. Only very few number can come out. So now here it is the vapor pressure of the solution. P1 is the vapor pressure of the solution. P1 naught is the vapor pressure of the pure solvent. This is for solution and this is for solvent. So what is happening here? The vapor pressure of the solution is becoming less. There is some relative lowering of the vapor pressure on addition of this non-volatile solute to the solvent. So you can able to see from the number itself, right? So 1, 2, 3, 4, 5, 6, 7, 8 solvent molecules are coming here, but here only 4 are coming out. The other things are getting blocked by the solute particles. Okay, so there is some lowering of the vapors coming out from the system. So there is a relative lowering of vapor pressure for the solution on adding the non-volatile solute molecule. Okay, so this is the concept. And from this concept, we are deriving one formula which will be very useful for solving the numericals. All of you should take down that formula. Okay, it is P1 naught minus P1 divided by P1 naught, which is equal to W2 into M2 by M2 into W1, where W1 and W2 are the masses of the solvent and solute. M1 and M2 are the molar masses of the solvent and solute. Okay, 1 means it denotes solvent everywhere. Even in your book also, 1 denotes the solvent and 2 denotes the solute. Okay, so W1 means mass of the solvent. M1 means molar mass of the solvent. W2 means mass of the solute. M2 means molar mass of the solute. That's all. Okay, you don't have to get confused. 1 is solvent, 2 is solute. That's all. W means given mass. M means molar mass. That's all. Everything will be given to you in the question. And what is this? P1 naught. It is the vapor pressure of the pure component. That is the solvent component. And here P1 is vapor pressure of the solution. Got it? So I hope the equation, the formula is clear to all of you. So let me solve one question for this today's session. Okay, and then I will end up. So I hope you all have noted this formula down in your notebook. Shall I go for the question? Are you all ready? Keep your notebook, pen, pencil, everything with you. You guys are going to solve. Yeah. Here is the question. The vapor pressure of water at 20 degrees Celsius is 17.54 mm of mercury. Okay. When 20 gram of volatile solute, non-volatile solute is dissolved in 100 gram of water, the vapor pressure is lowered by 0.3 mm of mercury. What is the molecular weight of the substance? What do you mean by substance? What do you mean by substance? Is it a solute or solvent? What is substance? Substance means solute, right? And water means it is a solvent. Water means it is a solvent. So these are the two components. Water is a solvent and substance is a solute. Two. The vapor pressure of water is given. And the formula which we are going to apply here to find out the molecular weight is this. Okay, molecular weight of the substance we are going to find out means we are going to find out M2. So this is what we are going to find out. Okay, what is given to us? We have 17.54, which is the vapor pressure of water. Water means solvent. Vapor pressure of water, pure component P1 naught, which is equal to 17.54 mm of mercury. Then what else we have? When 20 gram of a non-volatile solute. The substance is that solute. Okay. So its mass of the solute is 20 gram. If something is given in terms of gram, then it denotes the mass, given mass. Mass of the substance is given. If it is dissolved in 100 gram of water, water is a solvent, 100 gram is the mass of solvent, W1. Okay, 100 gram is the mass of solvent. The vapor pressure is lowered by, vapor pressure is lowered. There is decrease or relative lowering of the vapor pressure. Okay, so means P1 naught minus P1. This is the decrease, or I can call this as delta P. So that delta P value is equal to 0.3 mm of mercury. Now what is the molecular weight? Aishwarya has got the answer as 3.6. Okay, let me check. So guys, have you understood like how to approach it? We have P1 naught, we have delta P also, we have everything. We have W2, we have W1. You know how to calculate M1, right? 1 is water, M1 is the molar mass of water. How to calculate the molar mass of water? For hydrogen it is 2 and for oxygen it is 16. So the molar mass of water is 18. So we have M1 also as 18. So on substituting all the values, we can get the answer. Okay. So let me substitute. P1 naught is given. Change is also given. Mass of the solute is given. What is the molar mass of the solute? If the molar mass of solvent is 18 gram and the mass of solvent is 100 gram. These are the given values. Just substitute everything and rearrange it. You will get the M2 value as 210.48 gram per mole. Is it clear to all of you? This is straightforward substitution only. What you need to do, just practice how to find out the given values from the question. Okay, it is easy. If you understand the question, you can easily get it. You need to find out the solvent and you need to find out the solute. Okay, you need to find out the given values and you can directly substitute. You will get the answer. Is it clear? Okay. Okay, students, thank you so much for your patience. So till 5:15, you guys have attended. So from next class onwards, try to join on time, okay? So that we can discuss more things. So we are left with the 3 more colligative property. And along with that, we have one topic which is Van factor. So we may complete this lesson in the next class. All right. Thank you, students. Thank you so much for attending the today's session. Meet you all in the next session tomorrow. Okay. Take care. Bye bye. Thank you.